This
See that?
conference will now be recorded.
Yeah, was waiting for that cue. We are on record. Ahmed, please kick it off. Ahmed? Okay, I guess there's some difficulties and we'll allow him to fix it. Okay, so for the meeting today, I'll kick it off. We had planned four topics to go through, each about 15 minutes. So the first one is updates on Facebook's timing card implementation, and then followed by Aurelia timing card implementation, and then NVIDIA's timing card implementation. Last would be closing remarks from El Proma. I see you guys are on. Hi, thank you for joining today. And without further ado, let's go to Facebook's timing card, and I believe Oleg, you will be taking this one.
So Ahmed is supposed to join. I'm a little bit sad he did not join yet. So
Right.
I can try. I mean, I have a copy of the presentation, so I can start kick it off. And yeah, if you allow me to share the screen.
Oh, I need to do that. Yeah,
please,
sure.
Please use the Dropbox one. I don't know why I don't have this share screen.
You are the presenter now, Oleg, and go for it. Ahmed, if you want to be a presenter, I can set you as well.
Yeah, if you can set me up so I can get the share screen, I can do it from my end.
Perfect. So you're now the presenter. Go for
great.
it.
Share.
We have 13 minutes, let's say, before we go to Aurelia. Who will be presenting from Aurelia?
That would be myself, Jean-Arnold, and Laurent Borgani.
Great. I'll send you the presenters right after. Thank you, Jean-Arnold.
Just a second. There is one little here. Okay. And okay, let's see if that works now.
Ahmad, it looks like you're on mute.
Can you make me a presenter again, please?
Sure, here you go.
You are the presenter.
Okay, great. So let's see. So let's see if we can do it now. Okay, great. Finally. Okay.
That's good.
So I think you have the view. Okay, so we have, again, before I start digging deep in this, we have already like this discussion that we want to change the name to something more inclusive. So for now, for the time being, we just got Grand Main Clock, so we can keep the GM, and then we'll basically have this discussion about the name in a different time. So starting with this block diagram, we think that this is everything you need to build a grandmaster. This is basically the general picture. Like you need a GNSS, you need a high stability oscillator, you need a network interface, obviously, and some sort of logic and processing in the middle that can be interpreted with like whatever basically the need is. So and then there are different pathways they can exist or not based on your implementation. That like we try to make, again, this is like a general definition of like what you need to have in order to build a grandmaster. So the simplified approach is if you just use, let's say, a GPS disciplined oscillator, which they're like you can get them again from something very cheap all the way to more like elaborate solutions, which they basically incorporate the GNSS or GPS receiver providing the PPS signal to basically do this thing called disciplining the oscillator. So you do the disciplining of the rubidium clock or OCX or TCX or whatever is available there while GPS exists. And when GPS is not available, you continue basically your holdover with your clock. So as I said, like such things exist as like off the shelf, and you can just use them. And then you get the via USB, let's say the TOD and the PPS. So the PPS in this simplified approach should go straight to, let's say, to the PPS input of a NIC, like an off-the-shelf NIC that is able to do the external timestamping. And then you can get via USB basically the TOD. So there is already a tool, the TS2PHC, that can basically give you relatively good results for, as I said, like a simplified approach to build a Grandmaster. So this was basically our first take. We did this. Like on the left was like the big mess when we started. Like obviously a lot of these off the shelves. I opened them and I was trying like to see compare different oscillators. See like there's OCXOs like from two different vendors. There's a rubidium clock, and that keyboard actually is on purpose sitting there because it was supposed to keep the airflow for these servers. If you keep open these servers, like you need to cover where top of the CPU, otherwise you will have overheating of the CPU. So then with some like let's say refinement and wiring and everything, it became like this. And then we got like some good results on this. So a more reliable and more elaborate, let's say, solution is, let's say, this approach that we have like with a timing card. So with a timing card, all this, the GNSS and the, let's say, the high stability oscillator and that logic and everything goes basically on one card, and the card communicates, let's say, via PCI Express to the host. Why? Because in this approach, we thought that we put basically a PHC, the physical hardware clock, on the FPGA, and it gets advertised basically to the host as just like another PHC, like an ordinary NIC, but just PHC. And all the synchronization, the synchronization, the adding basically the TOD, everything happens basically on this FPGA, on this card. And then from your end and the host, you can use just a simple tool like, let's say, PHC to sys, which is a good copier for PHCs. And you copy this PHC into your PHC and you can continue. And you can also like approach it with different things. So we started like the development of this board, and the work is definitely work in progress. So this is like the first, I'll say, 3D model of like what we got like of the design. So we have basically the, as you see, like it's a PCIe form factor. You have a GNSS receiver, or you can put more, like you can put 2 for increasing reliability. The FPGA, we decided like to go with a swappable module, so you can, let's say, go with different vendors, go with different specs, performance, or whatever. And then we added like SMA connectors and also SMB connectors on the board if you want to keep all the wirings inside the case for 10 megahertz and PPS input and output. And then we added also a backup power controller. Let's say you want to, instead of like keeping all the hosts up or something, you can have something just keeps the Mac. By Mac, I mean miniaturized atomic clock. Or you can swap it with an OCX or something. Keep that one up for like some power interrupt. So the clock and the TOD basically keeps staying up. And again, we chose this form factor, this footprint, to make it easily swappable between different options depending on the need, like either OCXO or the Mac. And then we also added some dedicated TDCs, like time to digital converters, to, again, for various applications, VCO, PLL, and this microcontroller controlled crystal oscillators, like these smart oscillators, basically. And then we added also some environmental sensors and like even an RTC to again for different applications if someone needs, like this board can be versatile enough. So as I said, this board is completely hardware and software open source, and we welcome anyone to basically derive their own interpretation and changes or whatever they want to do on it. Fully compatible with TS2PHC and PHC2Sys, so you can even do external timestamping with this. And as I said, like the PHC will get advertised on the device tree like an ordinary NIC. And the versatility, as I said, is here. You can change it for whatever you want. So we did some testing also. So we put basically our open source Grandmaster connected to a transparent clock enabled switch, and we have these 5 machines. So these 5 machines, they run, and there's a 6th one that basically just collect the data. So 5 machines, what they're doing is they're running PTP4L, then they have the PPS input. So the PPS input for all of them is connected basically to a cesium clock. And they do external timestamping, and they send the packet that's basically the stamp that they get from their PHC to one machine to do the comparison. So in when you run everything fine, you see like basically this is the external timestamping for the first, second, third, fourth, and fifth machine. So what you notice here is the changes are only in the first 2 digits. That's in nanoseconds. So everything else is pretty stable. That shows you the synchronization is working very, very well. Next is you send all these machines basically to one, and again, in a bad day, basically, the steps, they don't look like, changes are only in last 2 digits. You will have changes all over the place. So again, you send all these timestamps basically to one machine. In that machine, you do the comparison. So you see like the first machine comparing with itself is 0, but with like the second one compared to second machine, like and so on, you see like all these differences all are within less than, I'll say, 20, 30 nanoseconds. So this is your synchronization. And on the right side, you see basically the Grandmaster tuning with the PPS input pulse, basically. And Oleg, would you like to quickly go through this?
Yeah, we don't have much time left, but I just wanted to say that the hardware itself is one part, but the software is extremely simple on this end. So the only thing you need is to configure a couple of services to run with systemd. Like in this case, we use TS2PHC to copy from the serial port, the NMIA, the data, and discipline basically the clock. And the whole topology later on looks just by configuring PTP4L and pointing, we're using unicast in our case, so, and pointing them to different master servers. This is extremely simple and does not require too much skills actually to bring your own PTP4L setup in the data center. Right. That's basically it.
Without further ado, let's continue then handing it to our colleagues in Aurelia.
Okay. Hello, everyone.
Hello.
Good evening for the Europeans. Hello for the Americans. Elad, if you can make me the presenter, please. Okay.
Please try now.
Not yet.
Okay, you should be on now. I pressed the OK button. Yeah.
That's perfect.
Thank you,
Okay.
Ahmed.
Let's go. So I'm Jean-Noël Chenio, Senior Program Manager, and we'll be talking today with Laurent, Technical Director for Aurelia System and Solution in Paris. The first slide is quickly to remind what we are presenting here and the goal to bring the accuracy to the core of what is normally a PTP network and what we wanted to design is a commodity card, something that you can put in way much server that you usually do, and to bypass when it's needed because your accuracy matters, or because you want some added redundancy. Put some timing directly into the server, so it can be used obviously into the open time server, or whatever name we'll use in the end, but it's also something that you can use in any other server that would need it. We take here the example of database servers that normally use PTP to connect to some grandmasters, and you know that better than anyone, but the number of switches, the way the network are usually designed make it sometimes tricky for PTP to be accurate enough, even if you add those layer of boundary clocks and transparent clocks. That's still something that can bring some additional error. And if you really want to bring the error to something very low, the best thing is to add some timing piece directly into your commodity servers, and that's what we are introducing today. It's what we call the atomic reference time ART card that goes directly into your servers, your own servers. On that, I will leave it to Laurent.
Hello, thanks, Jean-Noël. So, as he said, we basically started from scratch to think about this architecture. The approach was very simple. Keep it very, very simple, the most simple as possible, especially from the hardware side. So what we imagine is a PCI Express board, which is because it's a very convenient form factor to go into any kind of server. And then we just need to put the bare minimum hardware, which is needed to feature a grandmaster. So we considered putting any kind of oscillator, from a quartz-based oscillator such as OSXOs or CSAC, or even our new mini rubidium atomic clock, which has a form factor compatible with this kind of board. Then we can have one or two GNSS receivers, probably off the shelves. That's something we can buy everywhere. And the bare minimum, let's say, FPGA to implement the basic logic in order to generate timing and frequency inputs, generate outputs, and make the bridge through the PCI Express bus to go on the softer side, let's say on the host side. So that's the very simple hardware-wise approach. Of course, with this kind of hardware, we can also feed, for example, any NIC with a direct PPS, and we can use any external timing reference, either PPS or 10 megahertz, in order to be used in addition to the GNSS, for example. And the goal is to be able to use the local oscillator alone if there is any problem with GNSS, or to switch to another reference, which can be an external if necessary, if available. So that's for the hardware side. And then if we look at the software side, can you jump, John? Yes. So a little pause on the new micro rubidium oscillator that we launched recently. So it's a perfect fit for this kind of application because it's you probably noticed with the picture before. The form factor is exactly the PCI Express form factor ALF 8, I think. So it's a kind of coincidence, by the way, but it's nice because it's small, low consumption, but with the kind of rubidium frequency standard accuracy type. So I think it's very nice for this kind of application. So now if we jump more on the software side, so that's what's going to run on the host server. Because we want to have the bare minimum hardware, which is always a bit more specific, and to stay within, let's say, the philosophy of the open source thing, all the logic will be software side. So we will leverage as much as possible open source packages such as GPSD for GNSS management, and also all the PHT2Cs and so on and so forth, PTP for L, Linux PTP for to get to have this card seen as a kind of specific PHT device. So we'll have a driver, we'll implement a PHT device, and then from there it's easy to run PHE2Cs or the opposite. And then we will still need a daemon that will be a specific daemon that will implement the discipline logic and make sure that what the logic is making sense depending on the circumstances. Especially, do we have GNSS available? Yes, no. Can we discipline? Can we go on holdover? Is everything ready? For example, the oscillator, is it warm enough? The GNSS, is it working okay? So we can implement all sort of logics here on the software side in order to make it very easy to maintain, very easy to deploy, and scalable, because it's always easier to upgrade on the field software rather than FPGA or any kind of hardware. And the logic from our experience, the logic to basically entertain the complete card, meaning the different sensors like the GNSS and the atomic clock, is not that easy sometimes. There are some tricks here. So it's better to keep that on the softer side. So there will be a daemon that we call hard daemon that will just take care of the specific of the board on the hard side. So it will be easy to maintain. And then, of course, we can provide any kind of like basic API for this daemon. So we can have like a C API locally,
Hi, folks.
a REST API. Sorry.
This is Rajiv from Open Compute. Hi, Lauren. So, Ahmed,
Yeah.
I had a question. For this card that the Aurelia is presenting.
Yeah.
I mean, how does it link with the tab project? I mean, what is the intention? I mean, is it something that is going to be contributed, or?
Yeah, so you put that into any kind of server, and you can turn your server into a grandmaster.
So do you plan to contribute this card to Open Compute?
Yeah,
potentially, yes. That's why we're here. Yeah.
Okay,
Yeah,
I just wanted to make sure that we are not discussing any card information that we don't have any plan to.
Yeah.
Okay.
One quick clarification. Again, I should have clarified right in the beginning, but we had all this interrupts and whatever. So the thing is, like, we came up with this form factor that we want to basically approach this problem with a timing card. So the driver is something that we provide from our end. So we have like basically all the IOs or whatever it's needed and so on. So we have this standard form factor to basically liberate this grandmaster piece in like basically a PTP network. And now we have different basically vendors that they have their own approach to get to this.
Okay, that helps, Ahmed. That really.
Let's continue because we are on a tight time. Okay, go ahead. Go ahead, Laurent. Or Arnold.
I think technically speaking, we're done, and I think maybe to answer. It's a concept. It's somewhat similar to what Ahmed's described before. Different flavor, if you want, because I think there is less hardware on our concept than in Ahmed concept, but it's more or less the spirit of PCI Express form factor to turn in an open grandmaster into a grandmaster.
And definitely the goal is to contribute to the OCP-TAP initiative, and why we design it that way. That's because we don't want to have any FPGA locked code that can be sometimes a bit hard to make it live with the obsolescence of FPGAs, and that needs some rewrite and so on. So we rely on very small and sometimes open free IPs blocks on the FPGAs to do the job, and the rest is open source software. So the hardware is pretty simple. It's easy to make it evaluate when the FPGA becomes obsolete, or the clock, or the GPS receiver, and the rest is yours. You have the code for all all those daemons, and you can make them evaluate with the time.
Arshan, this is all correct, but Ahmed, again, going back to my original request, is I think it's good to first get commitment that these are the expectations that from you guys that OCP should expect to have it in the next few months or so before presenting it, because this really helps, because I wasn't aware of the fact that we will deep dive into these specifications for a card that I literally had no idea on. So, but I can take with Ahmed offline.
Yeah. No, we have already like a GitHub. On the GitHub, basically we put the specs, and then we had like a lot of like engagement from different again vendors to approach the same like a solution for the same problem.
And I can add that all these ideas are, I mean, the implementations we've seen so far, and we're going to see another one, are different, but they have the same commonality. I mean, if you look at the draft spec, then they all address these requirements, and we need to see what becomes mandatory and what becomes optional. This is still work in process, right?
Okay, understood. It's still nothing has been finalized yet. You're just trying to cherry pick different
These
solutions.
these
Okay.
are
Yeah.
proposals.
Proposal. It's okay. Got it. That helps. That helps. All right. I won't take much time, guys. Carry on.
Thank you.
And just to it's going in your direction, Rajiv. The thing is that what we are presenting here is not a product. It's not an earlier product. It's a concept. That's something that we want you to lead with the OCP TAP initiative. And what missing in for that to be a reality is two things. First, some industrialization, and the second one that most of you would require is CE marking on the product. That represents some costs, and because it's open source and community project, what we plan to do is to take the example of crowdfunding and gather interest from OCP TAP participants before going further. Because we believe that this will match the OCP TAP requirement, and we want it to be matching completely those requirements. We won't go further without some people on board, some quantities that could help to put this product to the market. Meaning that if we go quick enough, we could have the first deliveries in the first quarter of 2021. But if it's not matching the requirements, then it's done, and we won't go any further. So that's really the principle in which we are working, is really to be sure, and that's why also we are presenting it tonight, to get your feedback on this kind of approach. And let's see if it matches what would people in this initiative expect, and there we'll go ahead in the near future. So
Sure.
that's it. That's it for us. I think we are on
Wonderful.
time. So thank you, guys.
So let's go.
Yes,
Let's
yeah.
go next with NVIDIA.
Yeah, so Dotan Levy will present on behalf of NVIDIA. Dotan, I made you the presenter.
Thank
Please go
you.
ahead.
Tell me when you see my screen.
Not
Not
yet.
yet.
Okay.
Now we can see that.
So just as a general concept, because I listened to several questions that came up, the entire idea of the Open Grandmaster initiative is to limit as much as possible the moving variables of Grandmasters, such as accuracy, stability, and price, and make all the other a common commodity as much as we can in open source equipment. So what we did in NVIDIA, we make we have our own portfolio of card adapters, what we called cloud grade, and we made two additional OPNs. You will see them right away. That actually here to accommodate all the telco specs and the PTP stuff and the accuracy stuff, and actually they will be like 1/3 of this Grandmaster solution. And now we will see the combination between the NIC and the SIM card. So we have two different flavors. One of them, as you see, you can see that we added to the bracket the PPS in and out. So this is our commodity NIC, F-height, F-length. And we have it with the tall bracket and short bracket, etc. And we have this additional flavor that comes with the time card on actually on the module itself, so it doesn't consume additional rack space, additional slots, and we just piggyback our time sync card. And I will specify how do we do that. Not sure. Yeah. Okay. So we have we assembled an M.2 GNSS module. We found a commodity one, and we approached several vendors to create more flavors of it in different accuracy cost working points. This M.2 is 42 by 22, and it gets power from the adapters. It's fed for the Jeep. In that case, our PPS in SMA connector on the bracket is switched to be a GNSS antenna in, and it will feed the GNSS module. And the GNSS module will discipline the NIC. Well, the NIC, I don't know if you are familiar with our design. In our design, the PTP hardware clock is within the NIC, so it can accurately timestamp all the packet coming in. So the GNSS module will discipline the NIC using PPS, using SMA connector, and the time of day will be via the I2C bus. And this specific GNSS module contain an OCXO oscillator and a multi-constellation GNSS module in not the series that went out lately, like Series 8 from U-Blocks, if you're familiar with. So if you, for example, if you want to use a GNSS module, a sync card, it's not a GNSS module anymore. Once we form factor it like this, we call it a sync card. So this is a TAP sync card. So if you want to use Facebook sync card, or you want to use a Proma sync card, you can do it with the second OPN. So in that case, the card will have a PPS input into our NIC, and the time of day will go directly to the software on the server. Whether you use USB or PCI or UART or whatever you chose, everything works with open source. Actually, we prove it on lab. And if you want to go for space reduction, or whether you see this OCXO option fits you, we can use that. So actually, we have here, I think, a full variety of, I would say, yes.
I apologize, I'm too picky today. I don't know why, but this slide 9 has the NVIDIA confidential do not distribute footer at the bottom left.
Yeah, that's okay. We are sharing this.
We will remove the footer before we post it online.
That's okay. This is something that we share.
But our sharing is fine, but what is being shared says it's not to be shared. But we can again work on that offline.
Yeah, it's a mistake that I made. I didn't remove the footer.
All right, please go.
When we will publish it, it will be without the footer.
Yeah, but let's review going forward, before we present. That's all I'm saying.
Sure, we'll take it. Noted. Please proceed.
Any other questions from the crowd?
Yeah, Hisham has a question. So Hisham,
I have two questions actually. You mentioned that you support TSN shaping algorithms and policing algorithms like QBV and QCI. And do you support these algorithms in the RAN, the radio access network, over the cellular interface?
Yeah, it's not directly related to the topic that we are presenting here, but yes, we are supporting those profiles, those standards.
You support them on the cellular interface?
On the what?
Cellular. Between
cellular interface? No. This is on Ethernet.
Okay, good. And so you don't look at the propagation delay compensation to
we do over Ethernet. We are doing PTP over Ethernet.
Yeah, but do you to provide time synchronization end to end like in 5G, you need to compute the propagation delay compensation. How you do the propagation delay compensation? Using timing advance, for example, or using something else?
I think I don't understand the question, but we can take it offline because I don't think
Yeah,
it's in the scope of the presentation. Please feel free to approach me, Isham.
yeah,
Hisham and Dotan, I will create an email loop for us. Let's use
please.
yeah.
Yeah,
Let's
it
use
is a
that.
simple. It's a simple question how you compute propagation delay compensation
Yeah.
on the over the RAN. That's all.
Okay.
So one question, Dotan, if I may ask. So
sure.
like in case of you go with basically what is in the picture, like you go with one shot and you want to like use this one card, the holdover, how is the holdover maintained here? Like what's the OC, like is there an OCXO on the card as well?
So there is an OCXO on the GNSS, and it's actually it doesn't. Okay, the holdover in the telco is different than in the data center. We see wander requirement and jitter requirement. The OCXO should solve and stabilize the wander thing, as it's only stabilizing on a PPS output sync element. On the NIC itself, we have additional oscillator, which we don't expose here. We have an additional oscillator that manage the short-term, not short-term, sorry, low frequency, high frequency stability, the jitter. So we have additional oscillator.
So I mean, like, is there an OCXO on this card?
On this GNSS module, yes, there is an OCXO.
Okay. So in case, let's say you have
Not
a
an
different
atomic clock,
requirement.
yeah.
Yeah. Is there an option that you can add that?
Add what to the presentation?
No, I mean to the card. Basically, you feed the instead of an OCXO, you want to feed with a rubidium clock or cesium clock. Do you have that option?
So we are approaching other vendors, but it seems that it's very limited space here. So I don't know what will come up.
No, I mean like externally. Like let's say you add a. Is there a possibility to add that as well as an option?
Currently, no, but I think it's a valid point. I will take it with our engineering.
Sure. Thank you, Ahmed. Dotan, you want to cover time of day?
Yeah.
In the last
So
few
with
minutes we have.
So with respect to the time of day, the first implementation that we will have will be what we will decide here. I mean, the format that we will decide here in the tab. But we can add later on any other time of day. Those GNSS module can come to with software and they can do conversion. So we theoretically can do several formats here. The way that we transfer the time of day to the software, because the software itself is managing it, is that every time we get a PPS input, the PHC is being sampled on the NIC, and we send this event to the software. So software can see that the PPS event occurred at a specific PHC time and can discipline it. Now, this is respect to the frequency adjustment. With respect to the time of day, we also send an event on a time of day, which happens from every few seconds, and the software can do a set time command to our PHC in a similar manner to what was described earlier.
Dotan, can you use like let's say standard tools like let's say TS2 PHC and PHC?
We are using the TS2 PHC. We are using PHC to CIS. We are using PTP4L. We also tested with commercial stack and it also works. So everything seems to be very interoperable. I didn't. I wasn't familiar with the GPSD though. I will check it out afterwards to see if we can, what this module deliver and what we can do with that.
Dotan, do you have any maybe estimate when the first real prototype could be? For example,
Yes, Q1 2021 for engineering samples.
Maybe we can, if there is nothing else, Dotan, we can hand it to El Proma.
Sure.
Sure. Thomas, will you be presenting?
Yeah, sure. Can I get the access to screen, please?
Yes, you just got it. Thank you, Dotan. NVIDIA
Thank you.
going into Thomas El Proma.
All right, so good evening, good afternoon, good morning to everybody. So, do you see the screens now?
Not yet.
My goodness. What do you see then? Us?
Yes.
We
Yeah.
see you, yeah, in a social distancing.
Oh my God. All right. Screen. Oh, I don't know what goes wrong here.
If you have a PDF, I can share it
Now
instead of
it's a
you.
PowerPoint presentation. Go to system preferences. Well, unexpected things happen.
We have time. That we have.
Yeah, let's recover.
So one important thing in the top meetings is we're very timely. So
yeah, okay. I just touched the screen button on the button, but nothing really happened.
And then you have options what to share, and you're supposed to hit share button again. Maybe on your other monitor.
No, I have only one. It's Macintosh.
Macintosh.
Yeah, probably
we support Macintosh in TAP. No,
yeah. No, maybe you have to go in the preferences, and in the preferences you have to give it permission.
System preferences, and then nothing really happened here.
And then you have to go in
the preferences here.
In security and privacy, and then there should be on the privacy you should have like
Any progress now?
And now try it again. When you press.
I was going to say, if you also have multiple monitors, sometimes
He said he has one. He has one. Okay.
There are two people with one monitor.
They're definitely not socially distanced. I can see that.
Yeah. That's a good point.
Maybe they are seed family. I don't know.
Busted.
Are you there?
Yes, we're still here.
Now it should work. Try.
All right. How about now? Do you see presentation now? No.
No.
Okay. Well. Better.
Yeah, we got it.
It was waiting for the
Hallelujah.
Okay, let's
11:45. Go ahead.
All right.
Perfect timing.
Okay, we like to refer to several previous meetings, including ITFS and also the one we've seen on the LinkedIn and YouTube. So I will quickly make a short introduction, and I will give a voice to colleague, to Janusz, who will give detailed remarks. So the first of all, I want to come with the very good news that we can release open source a lot of GNSS receivers, which are the resolution T compatible. That's the standard you have chosen. We have the U-blocks on the board, including Neo, Lia, ZIT, which is a double frequency. But we also recommend some new receivers from the Japanese company Furuno. Especially, we want to highlight that this receiver is introducing to market a new multi-path mitigation technology that is really resistant for reflecting signals. Also, I think the members of the family who wants to make their deployments globally, including some East European regions, India, they might be interested in Asia manufacturer like Skytrack or CB-Top. And we have placed the one receiver made in Russia from the company NVS, which currently is in a production for many years, but it seems their development has stopped. So, okay, while we are showing all those receivers, there were several questions during the meeting regarding security. So I want to highlight a very important thing that is mostly forgotten, that time is born inside the receiver. So the receiver is receiving some telemetry data from the satellite system, but currently the UTC or atomic timescale is born inside the receiver. And that means that the accuracy and the stability very much dependent on the receiver. We have chosen only the best experience we have in the previous decades. So we will release those boards, open hardware and open software, whatever. What kind of problems you can expect dealing with the receivers? Well, the most frequent one is a leap second support, which is still, even the PTP is based on the atomic time scale. It seems to be quite a problem. Don't forget that if you follow the dependence on the other than GPS satellite systems, like for example, Russian GLONASS, the important thing to highlight is that the GLONASS basis on the continuous time scale, which means this is by nature the UTC, and the recalculation to the atomic time scale will require some arithmetical transformation. We know a lot of examples where the receivers behaves unstable, and what is interesting, the instability of the receivers frequently is not tightly related with the specific date of adding or subtracting leap second. The very famous manufacturer of the receivers in the previous decades, they noted some firmware problems that occurs many months before leap second and many months after leap second support. There are also other kinds of the problems that are related with the receivers. The most dangerous one are like the one noted on the 26th of January 2016, where the GPS SBN-23 satellite vehicle has introduced 13.5 microsecond error to the system. So those are the things that you should keep on in your head when you are considering stable solution. So I hope this slide can keep you memory on that. So going back to the free gifts we want to offer, the module on the left side, this is a development board. It's designed by Altroma team, so you can easily and quickly assemble any of the boards, and you can test it, using USB or RS-232 interfacing, including PPS. Also, I want to refer very shortly to some questions we met during the ITFS meeting. They were regarding jamming and spoofing. More of the receivers you see on the screen, they support kind of the error flag or alarm message indicating there is a jamming or spoofing attack. So the board can quickly be switched to the holdover operation, and it is definitely recommended to do so. But still, the solution the top project is designing is aware to use some active filtering of jamming and spoofing. You can see the example of such very miniature filter on the bottom of the page. This kind of the filters are requiring double antenna system, because all the detection of the false signal bases on many comparisons of the strength of the angles of the signal that are received by the receivers. So these are very short news from my side, and I am giving voice to a colleague of mine, Janusz, who will give you more details information regarding.
Thomas,
Yeah?
I have a question regarding the antenna. We definitely understand this is something that we challenge ourselves. We definitely understand the challenge when we go to telco market and you have like zillions of nodes and sites that you need to be deployed, but we are talking about data centers. Usually those POPs are very limited and very carefully selected in location. Is it fair to assume that we can liberate ourselves from this trouble? We will have an open sky access on top of our roof and that's it?
I don't know. I mean, you know, these days everyone is quite afraid for the cyber attacks. There are some definition of time synchronization attack for the distributed smart grids, for example. You know, they also have the same properties as data centers. So I think we can expect kind of the cyber attacks also to data centers. And that is what some first cases are unknown, but they are not really a good case study available on the internet to learn about. But we know this is going to happen.
So when you say cyber attack, you mean jamming and spoofing? I wouldn't consider that.
Jamming and spoofing, but also, you know, having flexibility on all those receivers I am presenting is quite important, because to ensure the time domain operation and frequency domain operation on a large scale of the country size, very much dependent on the firmware revision numbers and type of the chips that you are going to use. It's not as simple as it seems to be.
I agree with you. Jamming and spoofing are important for data centers for sure.
Yeah, definitely. Okay, let Janusz explain.
Nice. Oh my goodness. Somewhere. Okay.
He needs to move some pictures away.
Maybe this.
Okay.
Okay. Let's see. No. Okay. Now there is a difference between synchronization your Grandmaster card and network card, and in case of synchronization over PCI Express PTM, you can do something like cross-tie sampling, and this can allow you to average errors and eliminate problem because you have 8 nanoseconds trigger and some capture resolution. And also PTM allows you to compensate cable delay, so you don't need to do cable calibration in case of PPS cable. Now, in previous presentation, you show PLL inside FPGA. Such a PLL is more noisy than external one. Another thing, you connected directly 10 megahertz output to your local clock, and it seems it is not controlled, not tuned, so it is rather free run. So you cannot output 10 megahertz when you are using 10 megahertz input. And another thing, you change frequency using PTP hardware clock counter. This has some disadvantages like sawtooth effect, and you have a bigger jitter on 1 PPS input on capture. Here's an example of the jitter and also sawtooth effect. And one thing more, on the picture there is no filter to implement the second order PLL. So the question is in the picture, on the picture, how you are going to implement synchronization, exactly synchronization. And another thing, here is example of frequency adjustment when you can achieve fractional tuning using some patterns like on the slide. Okay, better thing it would be tuning using digital PLL or directly tuning your local oscillator if it's digital, so you can control it digitally or over DAC. And here's a difference. In case of 10 megahertz inputs, you can divide the frequency and capture, for example, as 1 PPS or something more frequent, and then monitor and also synchronize to the signals because you have quite stable oscillator. Okay. And there is a question: what is goal for a 10 megahertz output for you? Because it depends how to implement the board is the best. And another question is for 10 megahertz input. What is your clock reference? Is it a reference like a session clock with a frequency offset, or it is corrected? Frequency offset is corrected nearly zero, like from EPMPC.
So I can quickly refer to that. Like the 10 megahertz input is basically another option if someone wants to use, let's say, again, this is like we're trying to build something that everyone can use, like a wide variety. And then the 10 megahertz output was more for measurement. And let's say in case of, let's say you have another application that you want to use this card to synchronize another card, then you can use basically this one as an output to daisy chain, like let's say various things. It's just like another way to do things. For example, I have the external timestamping here that you can use this for other applications as well, because it's not only data centers. Like we're trying to make this as versatile as possible. Like we have a VCO PLL on this that can get, like, essentially you can implement this or like assist an implementation with White Rabbit on this. So again,
yeah, we definitely think more general on your
exactly.
idea.
It's a general. Let's go ahead. Sorry.
Okay.
So that's the, if you can
I
take
think
one.
also we are not, I mean, 8 nanosecond time error is not a goal for a grandmaster on a data center. We care more about stability and holdover.
Yes.
I think we should mention, Ahmed, maybe what is our goal in terms of time absolute error, or at least in general, let's take.
Yeah, it's quick because we don't want to take from their time. I want Alproma to finish as well.
Sorry.
Yeah, let's go ahead and we can.
Okay, shall we continue then?
Yes, please.
Yeah, go ahead.
Okay.
Last 2 minutes.
But good resolution is important if you want to quick synchronization, because you can observe your source in much shorter period and synchronize to it. Here's an example when resolution causes you don't see much smaller frequency offset before for for hundreds seconds. And in case of the board, you can also consider to use super LCD as it's more stable for temperature, but cold over is much better with rubidium oscillator. This slide is not actual after your today presentation, as you included temperature sensors. Well, and here is it is better to use to connect 1 PPS directly to FPGA also, not only multiplexing the signals, because then you can monitor time error to the potential time source before switching on, and also this could allow you to implement ePRTC.
Sure.
And there is exactly the same thing with 10 MHz input. You can connect directly to FPGA, and as I showed before, you can divide the clock and measure time error, and then observe and synchronize to the external clock on the correct frequency offset. One word about another your presentation. Of course, when you have two sites and one site has no GNSS, SyncE allows you to reduce noise on site A in this case. So the sites will be better synchronized. And another things why we talk about ePRTC, when GNSS failed, you have jamming or spoofing, and there is no link between sites as here between A and B, but other communication is available. The sites can be still well synchronized, and there will be no time islands. Thank you.
Okay, and I want to end, I start with some timescale information, and I want to end it with the information that, for example, if you synchronize yourself on the node A to the GPS and node B to the GLONASS, you will note it by nature of the timescale recalculation offset something like 30-40 nanoseconds, because that's the natural offset between the Russian timescale and the US naval timescale. Okay, thank you very much.
US is ahead or Russia is ahead?
Sorry?
Who is ahead? Who is more advanced? No, I'm kidding.
In time.
In time.
Okay, thank you very much, El Poma.
Thank you.
We've seen today very different implementations. Thanks everybody for sharing, and let's let these things sync and offer a chance to everyone to collaborate offline with any questions or follow-ups.
Yes, thank you, El Poma, for your comments. We will address them. Thank you.
Thank you, everyone.
Thank you, guys.
Goodbye.
Goodbye. Bye.
Thank you.